Our topic for today's webinar is optimizing nanoscale feature analysis using modern AES systems. The ultimate motivation for this presentation is driven by the ever-growing list of technologies that rely on nanoscale features for enhanced performance. Of course, we're all familiar with Moore's law, stating that the number of transistors on an integrated circuit doubles roughly every 2 years, pushing the scale of semiconductor devices further and further into the nano regime. Nanostructure materials are also ubiquitous in industrial catalytic materials, which help provide us with cleaner air and energy. Metallurgical inclusions and grain boundaries on the nanoscale are of critical importance in corrosion studies. More recent scientific advancements include additive manufacturing or 3D printing and atomic layer deposition, atomic layer etching. These applications also heavily rely on the ability to accurately characterize features in the nano regime. Of course, one of the best characterization tools on the market for these types of features is Auger Electron Spectroscopy. So that brings me to the agenda for today's talk. I will start out with a very brief overview of Auger Electron Spectroscopy, followed by a few practical tips for users of the PHI 710 instrument. And then finally, the majority of the presentation will be about how you can optimize your nanoscale feature analysis with respect to different beam conditions. Here's a diagram I'm sure all of you are very familiar with. We see the interaction of a primary electron beam with the solid surface. And although the excitation volume caused by the primary electron beam is large, the Auger electron escape depth is quite shallow, typically about 4 to 50 angstroms. However, this large excitation volume also gives rise to backscattered electrons, which can greatly affect Auger analysis, and we'll discuss that in greater detail later in the presentation. One of the primary reasons Auger electron spectroscopy is the go-to technique for analyzing nanoscale features is that the signal comes from the top 4 to 50 angstroms of the sample surface, making it a truly surface-sensitive technique. Because of its extreme surface sensitivity and small beam size, AES can achieve an SEM spatial resolution of 3 to 4 nanometers and an elemental mapping spatial resolution of about 8 nanometers. The example here shows a gallium arsenide, aluminum arsenide superlattice with the Auger gallium map on the left and the Auger aluminum map in the center. If we extract line scans from these maps, we can see that we can distinguish a 4 nanometer line in the aluminum map, which really puts Auger at the forefront of surface analytical techniques with respect to spatial resolution at the nanoscale. Auger can determine elemental and in some cases chemical composition of small features in thin films. Here's an example of an inclusion in carbon steel that was observed in the SEM image. The corresponding Auger color overlay map shows the elemental composition of the inclusion. And in this case, some chemical information can be inferred as well. Notice that in the elemental map, we have pure copper in green, and we have oxygen in red. And there are certain regions where both oxygen and copper coexist, so we can actually distinguish from the map a chemical difference between copper and copper oxide. Since its early inception, AES has undergone several major hardware advances. In the early days, a tungsten filament was used, which allowed the beam to be focused down to say a micron or so. The introduction of the Lab 6 filament reduced the beam size down to the order of 100 nanometers or less. Today, we use a Schottky thermal field emission electron source, and the current beam specification is 4 nanometers. Detector hardware has also evolved over the years. Today, we use high-gain microchannel plate detectors, which offer much higher sensitivity than their channeltron predecessors. Our current Auger system, the PHI 710 instrument, also offers multi-technique capabilities such as EDS, BSC, EBSD, FIB. We have an in situ cold fracture and parking, 4 contact stage for electrical measurements in situ. And we also offer small and large transfer vessels so that you can move samples around from system to system without breaking vacuum. The multi-technique capabilities make it a very robust tool for nanofeature analysis. The first tip, which I'm sure most of you already know, is that for ultimate spatial resolution, the lower the main chamber pressure, the better. UHV is needed for 2 reasons. The first being that electron spectroscopy requires electrons to travel from source to sample and from sample to analyzer without bumping into other gas molecules. The second reason, of course, is that we need the sample surface to be kept clean throughout the analysis. Here are a few tips from Denny Paul, who I'm sure a large portion of you on this call know, and who recently retired after 46 years at PHI. And his tips are to put the sample in the main chamber for a few hours the day before you start the analysis, and then to cycle the sublimation pump twice at the end of the day before analyzing the next day. Just note that these extra steps are really only beneficial when you're trying to achieve the ultimate 8 nanometer spatial resolution of the instrument. Another handy tip is to let the beam sit at 20 kV overnight before you start the analysis. And if you need to use high voltage for your analysis, that is to let the beam sit at 20 kV overnight the night before. Because for some field emission tips, especially if they're at the beginning of their lifetime, it can take several hours for them to stabilize at high voltage. And again, this is really only needed if you're trying to achieve ultimate spatial resolution. This is a really obvious one, but I wanted to throw it in anyway, because occasionally we in the lab still make this silly mistake from time to time, and it's important to remember, and that's to turn off the in-chamber light source when you're doing high magnification analysis. There's a fan in this unit that causes vibrations that can be seen in the images at high mag, so don't forget to turn the light off. Another tip is to use the smallest aperture, the objective lens aperture. The 710 has an aperture plate that consists of 5 different apertures, a large one, a medium one, and 3 small ones. Usually the smallest aperture has been located and set by the service engineer upon system installation. However, if it's been moved around since then by turning this wheel in the upper chamber, it's worth just checking to make sure it's been moved back to the smallest aperture before you begin your analysis. The next tip is to make sure when you set up the analysis conditions, you're using image registration at least every 1 minute. At high magnification, it becomes extremely important to account for any drift that may occur over time. So the more frequently you account for this drift, the better. What we typically do in our lab is first set a cycle number to 1. Here are a few screenshots of the software. So we usually set the cycle number to 1 and then adjust the number of sweeps for each element to make sure that the run time is under 1 minute. And then we can enter the number of cycles we want to do image registration, image registration every 1 cycle, and we know that it's going to be done every 1 minute or less. If you have many elements or require high pixel resolution, you can choose to do image registration after specific regions instead of cycles to keep the time under 1 minute. My last practical tip for high magnification analysis is to ensure that the electron beam is centered by wobbling the X and Y stigmation. Of course, we're all, I'm sure, familiar with using the typical parameters, the focus, the stig X and stig Y to focus the electron beam. But here's a screenshot of what it looks like to wobble the stigmation in the software. In the SCM tab, there's a properties button under advanced controls, and clicking that will bring up this box. If you then right click on stigmation X, you can select start wobble. Then you can adjust the stig steering in X and Y to minimize the wobble in the SCM image. And then you repeat this process again for stigmation in Y. So now those are just a few quick practical tips for how you set up the sample in the chamber and a few tips for getting started. But But now you're faced with the question of what beam conditions do I use in order to optimize the analysis of nanoscale features. For the electron beam diameter, there are a few different trends at play with respect to beam current and voltage. This diagram on the left shows trends for the beam diameter with respect to beam current on the x-axis, and the different colors of the lines represent different beam voltages. Although this data is taken from a 680 instrument, the trends are the same today. As the beam current increases, the diameter increases. As the voltage increases, you can see the low voltage in blue and the higher voltage in red. So as the voltage increases, the beam diameter decreases due to reduced chromatic aberration and space charge effects. So I put together a brief summary of the advantages of high and low current, as well as the advantages of high and low voltage. So let's start with high and low current. For high current, really the only benefit is faster data acquisition. Low current, however, will give you a smaller beam size, you'll get less sample damage, and it'll be slightly better for insulating samples. For voltage, the advantage of using high voltage is that you get a smaller beam size and much better sensitivity to high energy Auger transitions. Low voltage provides better performance on bulk insulators, slightly less sample damage, and it's slightly better sensitivity for low EV Auger transitions. So you may be thinking that if I want to look at nanoscale features, I'd want the smallest beam size. And according to this information, low current, high voltage gives the smallest beam size and should therefore be best for nanoscale feature analysis. However, as we'll see in the next few slides, this is not always the case. For high spatial resolution elemental imaging, the choice of what beam energy to use is relatively straightforward. Spatial resolution for images is approximately determined by the beam size. So the conditions that I outlined on the previous slide for the smallest beam size, which would be high energy and low current, are optimal. This is because any backscattering contribution to the signal can be disregarded by expanding the contrast of the thermal pseudocolor image. And only enough current is needed in order to meet signal to noise considerations. However, what if you need to do spectroscopy in order to quantify the atomic concentration of nanoscale features? The story here becomes a little bit more complicated. So for quantification, scattering effects can greatly affect the accuracy. This figure shows calculated electron trajectories on a 0.7 micron titanium nitride cube in an iron pit. At higher beam energies, even though the beam is much smaller, such as the case with a 30 nanometer diameter beam at 20 keV, there's much more beam scattering. With lower beam energies, like in this example of 3 keV and a 60 nanometer beam, there's much less scattering. So the next several slides will discuss the effects of beam scattering in more detail. When an electron beam hits a particle, there are two scattering paths that can result in the excitation of signal outside of the point of contact of the electron beam. One path is backscattered electrons that result in the primary electrons passing through the particle into the substrate and reflecting back toward the surface. The second is lateral scattering of electrons from the primary beam out of the side of the particle and into the substrate. Both of these scattering paths can allow for the signal from the substrate to contribute to the Auger spectrum, as opposed to only getting signal from the nanoparticles of interest. To take a closer look at the effects of beam scattering, let's consider a 500 nanometer particle being impinged upon by a 20 keV beam versus a 5 keV beam. Even though the 20 keV beam is smaller in diameter, there is much more backscattering and will therefore be more signal coming from the substrate. The 5 keV beam, however, has a bigger beam size, but less scattering and therefore less substrate signal contribution. One way to measure how much of the analysis volume comes from the particle as opposed to the substrate is to look at their respective intensity ratios. If we consider an alumina particle on silicon, the intensity ratio of aluminum to silicon is a measure of how much beam scattering is contributing to the analysis volume. So ideally, we would want all of our signal to be coming from the alumina particle and none to be coming from the silicon. So a high aluminum to silicon ratio is preferred. In the case of a 1 micron diameter particle, we see as the beam voltage decreases, the amount of substrate signal contribution also decreases, which is in agreement with the Monte-Carlo simulation shown on the previous slide. Therefore, in this size regime, 1 micron diameter particles, lower beam energy provides more accurate quantitative analysis of these larger particles. What about smaller particles? As the particle size decreases, the story begins to change. Here, in the case of a 300 nanometer diameter particle, we see more substrate contribution using a moderate beam energy of 10 kV compared to higher or lower beam energies. In this particle size range, a higher beam energy may be better than a lower beam energy because there is a higher Auger electron yield for the high EV transitions using a higher beam energy. This will be made evident later in the presentation as well. Looking at even smaller particles, like we see here in the Monte-Carlo simulations of a 100 nanometer diameter particle, we see that using a lower beam energy results in more lateral scattering out of the sides of the particle, and therefore more substrate signal contribution will be given by this low energy beam as opposed to the high energy beam on these smaller particles. Here we show two smaller particles, the figure on the left being from a 100 nanometer alumina particle, and the figure on the right being from a 50 nanometer alumina particle. In both cases, the trend is the same, with the slope of the trend line being steeper for the smaller particle. We see that in the cases of particles about less than 100 nanometers in diameter, a higher beam energy is preferred as it provides more accurate quantitative analysis because there's less substrate signal contribution. Again, the trend gets steeper and steeper as you go to smaller and smaller particles. So clearly we see that higher beam energy is better for getting accurate elemental quantification from particles less than about 100 nanometers in size. But if you remember earlier in the presentation, I mentioned that one of the advantages of using lower beam energy is that it causes less sample damage. Here on the left is some data collected on an alumina particle that shows how the aluminum intensity at 52 eV changes over time. As the electron dose increases over time, the aluminum intensity at 52 eV is also decreasing. The table on the right, we can see that the electron dose and critical time measurement changes for different types of materials. So the effect of this electron stimulated desorption is more pronounced for oxides than compared to nitrides. We can see the critical time measurement is quite short for oxides, and you get a longer critical time measurement as you move into nitrides. Here's an example, a practical example of how this can really affect quantitative analysis. At 25 kV, there's a huge difference between doing 50 sweeps on a particle and doing 200 sweeps on a particle. As the electron beam impinges on the particle for longer periods of time, there is more electron stimulated desorption of the oxygen within the aluminum oxide. This results in a lower aluminum to silicon intensity ratio because as the aluminum gets reduced, the peak shifts from about 1380 EV to about 1385 EV. Therefore, we're moving outside of the analytical window that we've selected for our peak-to-peak height calculations. And that causes a reduction in the aluminum intensity as this peak shifts away from the aluminum oxide peak window. Spatial resolution and beam scattering effects can also be inferred from line scan data. This is an example of a line scan taken across a 0.7 micron titanium nitride particle on steel. The left line scan was acquired using a 20 KE beam and the right line scan using a 3 kV beam. We see that in the case of 20 kV, there's a sharper interface between the particle and the substrate. And this is due to the smaller beam size that you get with 20 kV. However, there's a large signal contribution from the iron-containing substrate due to backscattering. In comparison, the 3 kV line exhibits a less sharp interface, but much less substrate contribution. So that's a brief overview of the rather complex factors that affect beam energy and which beam energy to use with different size features. But what about beam current? Thankfully, the story with beam current is a little bit more straightforward. With lower beam current, there's a smaller beam size and therefore a larger aluminum to silicon intensity ratio. You can see in the diagram on the right for a 0.1 micron particle that the lower current data in pink has a higher aluminum to silicon ratio than the higher current data in red. This effect becomes more and more pronounced at higher energies. The difference between 1 nanoamp of current and 10 nanoamps of current is larger at higher beam voltages than it is at lower beam voltages. This effect is also more pronounced with smaller and smaller particle sizes. Another factor to consider when looking at nanofeatures with AES is the escape depth of the Auger electrons. Here we see a universal curve showing the correlation between escape depth and kinetic energy of electrons. From the curve, we can see that for the case of typical Auger energies, lower energy transitions have a smaller escape depth and therefore arise from shallower within the material. One might think that for analyzing small particles, the shallower the information depth, the better. However, again, this is not always the case. Here we have Auger spectra acquired from a 0.5 micron aluminum particle on the left and a 0.1 micron aluminum particle on the right. Both aluminum and silicon have two transitions to choose from when you set up your analysis. They both have the LMM transition at lower energy and the KLL transition at higher energy. If we look at the aluminum to silicon LMM ratio, we see that it is much less than that of the aluminum to silicon KLL ratio. That's because primary electrons can travel further, lose more energy, and still excite these LMM transitions where they would not excite the KLL transitions. Therefore, when selecting between high or low EV transitions and the quantification, when you're doing your atomic concentration of nanoscale features, higher EV transitions are preferred because they are affected less by backscattering. So everything in this presentation so far has been about raised structures, particles on surfaces. Of course, real-world samples usually do exhibit some type of topography. However, what about the case of flat features? These could be present in cross-sections, fib cuts, fractured samples, or grain boundaries. In this example, we have a flat surface consisting of titanium on the left, molybdenum on the right. And if we want to get an idea of the sharpness of the interface between these two materials, the best way to do that is to look at a line scan. From the SEM images, we can see that at higher beam voltages, the SEM image is a little bit clearer. You have a smaller beam size, you have better spatial resolution, and the spatial resolution tends to decrease as we decrease the beam energy because you're getting a larger beam. However, even though the beam size is smallest at 20 kV and the SEM images the sharpest, the higher beam energy doesn't necessarily provide the sharpest interface on the line scan. Here we can see at 20 kV, we have an interface size of 186 nanometers. We have an interface size of 103 nanometers at 10 kV and an interface measurement of 93 nanometers at 5 kV. Therefore, the lower beam energy gives us the sharpest interface in the line scan in the case of a flat sample surface. So just like with larger raised features on a surface, like we saw in the case of 500 nanometer particles, the large backscattering caused by 20 keV beam causes poor interface resolution compared to the slightly larger but less energetic beam. I would like to conclude today's talk with a summary in the form of a flowchart. And the purpose of this flowchart is to answer the question, which beam condition should I use? Start by assessing your analytical needs. In the case of high spatial resolution elemental mapping, high energy and low current provides the smallest beam size and the best spatial resolution. This is pretty straightforward. However, if spectroscopy and accurate quantification is needed, then we need to ask ourselves, are the features of interest topographically flat, or are raised structures present on the substrate? If the features are flat, low voltage and low current are best. If the features are raised, we should then ask the question, how large are the features of interest? In the case of larger particles, about 300 nanometers in diameter or greater, low voltage and low current are best. A side note here is that in the case of flat samples and these larger particles, the effect of using high current and low current is less pronounced. So you can kind of get away with using high current in these two cases without too much trade-off in order to reduce your analysis time. For smaller features of interest, around 300 nanometers in diameter and smaller, the best beam condition is high voltage and low current. A few other caveats to consider with these small features that were discussed in this presentation is that certain materials can be damaged by long dwell times, and high EV transitions are affected less by backscattering. Quite a bit of the data I've presented in this discussion has been previously published in these two references shown here. I also wanted to specifically highlight these two books, which are great references containing tons of information for Auger users.